world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality.
With him about the
All
first
right.
topic.
Hello and welcome everyone to Celestial Theodolite update number 29. Today we're going to get into some definitions, and that's about it. I don't have too much to go over here, but we're going to read a little bit from Umland to start us off, because we often talk about the conceptual models of the terrestrial and the celestial sphere. What exactly is meant by that, and geocentric coordinates are often referenced and stuff like that. So we're going to take a quick read through of the basics of celestial navigation by Umland. I'll put the PDF in the chat here in a second. Actually, put it up now. Oops. All right, the Umland doc is in the chat now, if anyone wants to reference it. Okay, so the basics of celestial navigation. Celestial navigation is a branch of applied astronomy. It is the art of finding one's geographic position through astronomical observation, particularly by measuring the altitudes of the celestial bodies, the sun, moon, planets, or stars. An observer watching the night sky without knowing anything about geography and astronomy might spontaneously get the impression of being on a plane located at the center of a huge, hollow sphere with the celestial bodies attached to its inner surface. Indeed, this is a naive model of the universe that was in use for a millennia and was developed to a high degree of perfection by ancient astronomers. Still today, it is a useful tool for celestial navigation since the navigator, like the astronomers of old, measured the apparent positions of the bodies in the sky, but not their absolute positions in space. What does this mean? Well, in the heliocentric current paradigm, the positions of the stars are many, many light years away. But for this conceptual model to work, you could consider them fixed to a equidistant web, like an outer shell, and that you're in the center of it, and the bodies move in relation to into you. So this is starting the backbone of relating these two, but we're going to continue on here to talk about the horizon of coordinates and how that relates to a hemisphere vision and all of that for this conceptual model to work, because that's what's being relayed here, right? We often talk about how we see in a hemisphere vision. Well, this is defined the same on in both models here. So as we continue to read here, we have the apparent position of the body in the sky is defined by the horizon system of coordinates. In this system, the observer is located at the center of a fictitious hollow sphere of infinite diameter, the celestial sphere, which is divided into two hemispheres by a plane of the celestial horizon, shown in figure 1.1. The altitude, h, is the vertical angle between the line of sight to the respective body and the celestial horizon, measured from 0 to plus 90 degrees. When the body is above the visible horizon from 0 degrees minus 90 degrees, it is below the horizon, or invisible. The zenith distance is the corresponding angular distance between the body and the zenith. It is an imaginary point vertically overhead. The zenith distance is measured from 0 through 180. The point opposite of the zenith is called the nadir, where z equals 180. H and z are complementary angles, so h plus z will always equal 90. The true azimuth, the a and z here, is the horizontal direction of the body with respect to the geographic north point on the horizon, measured clockwise 0 to 360. So the baseline of this is using a observer-centric fictitious coordinate system to describe a hemisphere of vision, and and that's going to relate to the angular change of the celestial body. Because in order for this celestial sphere here of an infinite radius to be useful, it has to be merged to the terrestrial sphere. So in reality, the observer is not located on a plane of the celestial horizon, right? This is the way that they would want you to conceptualize it on a globe. So the observer standing here, the sensible horizon and the geoidal horizon merge together, which is the sensible horizon is the horizon at your eye level. It's not like the actual horizon, and the geoidal horizon would be the actual geometric horizon, is if you could see it with no refraction, and the celestial horizon intersects at the equator. So your hemisphere of vision wraps all the way is comprised of this from where the ground meets the sky. All of that sky can be described by positions of the stars all the way down to the equator, essentially. So this is your hemisphere of vision. Okay, the celestial horizon. Let's see, I think the celestial horizon is the horizontal plane passing through the center of the Earth, which coincides with the center of the celestial sphere. The geoidal horizon is the horizontal plane tangent to the observer's position. The sensible horizon is the horizontal plane passing through the observer's eye. These three planes are parallel to each other. The sensible horizon merges into the geoidal horizon when the observer's eye is at sea level. Since both observers are usually very close to each other, since both horizons are usually very close to each other, they can be considered identical under practical conditions. None of the above horizontal planes coincide with the visible horizon, the line where the Earth's surface and the sky appear to meet. Okay, so the visible horizon is a little different, but that's where the ground and sky appear to meet. So everything up in the sky is going to be defined by this intersection of the celestial horizon, which is, would be outward from the equator. Okay. Calculations of celestial navigation always refer to the geocentric altitude of the body, an altitude measured by a fictitious observer being in a plane of the celestial horizon and at the center of Earth, which coincides to the center of the celestial sphere. So this is the merger of the two. The geocentric transformation is what ties the sphere of infinite radius to the terrestrial sphere, which is said to be the cause of why the stars change angular position in the sky. Because of the 60 nautical mile per degree relationship, you guys interpret this as physical Earth curve. Whereas our position is that this is just how we perceive it optically, and it doesn't have any physical meaning on the ground. Any questions so far about what a geocentric transformation is, or what the celestial sphere and terrestrial sphere models are?
No question, but the correction that it wouldn't be on the equator, it would be on the horizon. The equator, it isn't tied to the observer. It depends on basically the halfway point between the North Pole and the South Pole. And that is independent of the observer, regardless of what latitude it's in. The horizon moves with the observer. So it isn't related to the equator at all.
Sure, but an easy way to conceptualize it would be your hemisphere of vision relates to that, because that's where that's where you're going to have Polaris following that 69 mile or that 60 nautical mile per degree relationship, where it would be set at 0, right? So
Well,
it's
I
just
think we're confusing like the alt-as personal grid with, say, the equatorial grid, which would have the mean reference and put the relation between the two. I don't know if that's purpose, but there's definitely two different things.
Yeah, that was basically my point, that this is describing the alt-as coordinate system, not equatorial coordinate system, and the equator is a part of the equatorial coordinate system. They would only be equivalent if the observer was at the North Pole. If you imagine the observer at the North Pole, then his horizon would indeed be at the same place as the equator, as the celestial equator. But in any other case, it would be tilted relative to the celestial equator at some angle.
Or what about the South Pole?
And but you would still have that same relationship where the celestial horizon is the intersection / extension of that going outward. So you're still seeing the same section of sky is the point.
I think his point's just that it's not related to the equator of Earth. It's
Yes.
personal. It's different
Yes,
for every
exactly.
observer.
Okay, agreed. All right. So let's see here. Where were we at, lads? We were a little bit down here. Yeah. Okay. Since there's no way to measure the geocentric altitude directly, it has to be derived from the altitude with respect to the visible or sensible horizon. Altitude corrections are in chapter 2. And then the last part here we'll go through. So a marine sextant is an instrument designed to measure the altitude of a body with reference to the visible horizon. Instruments with any kind of artificial horizon measure the altitude referencing the sensible horizon. Altitude and zenith distance of a celestial body depend on the distance between the terrestrial observer and the geographic position of the body, the GP. The GP is the point where a straight line from the celestial body to the center of Earth intersects at Earth's surface. A body appears to be at the zenith when z equals 0 degrees and the angular height above the visible horizon equals 90 degrees. When the GP is identical to the observer's position. A terrestrial observer moving away from the GP will observe the altitude of the body decrease as his distance from the GP increases. The body is on the celestial horizon when the angular height above the horizon equals 0 and its zenith distance is 90, when the observer is 1/4 circumference away from the GP. For any given altitude, there are an infinite number of positions that have the same distance in GP, forming a circle on Earth's surface, whose center is at the line given here at CGP, below Earth's surface. Such a circle is called a circle of equal altitude. An observer traveling along the circle of equal altitude will measure a constant altitude and zenith distance of the respective body, no matter where he is on the circle. The radius of the circle r, measured along the surface of the Earth, is directly proportional to the zenith distance. So in other words, the way that you perceive this star being at a lower angle is physically because of Earth curvature. Would anyone agree or disagree?
I do agree.
Awesome. My freaking guy. All right. So with that premise in mind, what we can do is we can make geometric predictions on intersection timings which correspond to occlusions when a star gets occluded. Now, for definitions on occlusions and other things here, there is, let's see, where's my definitions? There we go. So if a definition is not covered here in the database, you can refer to this link from the military. They've got all the definitions here, and I don't disagree with any of them until otherwise noted. So assume that everything in here that I also agree with. But that is you can find those definitions there. And then when referencing the spreadsheet for the notation guides for everything, if you're curious of what something means, you can reference the notation guide here. And then if you're busy and on the go and you just need some background noise, you can go to my YouTube and type in Nicki Minaj and the Celestial Theodolite Update number 10, Nicki Minaj's Complete Guide to the Celestial Theodolite Math, where we went over the notation guide there. So all of those are available. Now, once we have our predictions here, we can someone's hot micing, please. Thank you, sir. So once we have our predictions here based off of physical elevation for mountain peaks, right? So on a flat Earth, we do arctan, rise over run. So we take the difference in elevation from the observer and the mountain, and we use that altitude as our rise. And then we have the run already. We have the distance there. Our distance is just calculated using Haversine and the radius given here of 6,371,000 meters. So we do have plus or minus error bars for these that are derived based off of averaging how they say that the North Pole has like a 20-kilometer difference in radius from the South Pole. So we took the difference of those for our averages and whatever. But anyway, just to keep everything straightforward, Distances are all calculated off of that and just using that as the fixed radius. Now, from this, we have an occlusion that occurs. And from that occlusion, we hop into stellarium and we reference where the true position of the star was with respect to the peak. Why do we do that? Well, the true position of the star is considered to be the unrefracted position of the star, or rather, it's like the light source of the star. And its zenith position was once measured as it was transiting someone's zenith at the first point of Aries. And then they added 15 degrees per hour to that zenith measurement. And that's the consistent location for that star. And then there is the apparent position, which is the position that we see, which is said to be affected by astronomical refraction, which changes that, which is said to be the cause of the angular change between those two, and specifically, when the stars get close to the horizon, they don't follow the 15 degree per hour relationship. They end up lingering or looming. So the explanation given is that there's, just more astronomical refraction that the starlight has to travel through, more atmosphere. So it lingers more. So we're referencing that true position as the light source, in the same sense that you would if you had a flashlight that you knew, when it was directly aligned with you, where there would be the least amount of refraction and difference between you and the light source, and then that light source was just to, start moving at 15 degrees per hour. The apparent, what you see, like the apparent position and where it actually is, would drift a little bit. So all we're interested in referencing is, where that true position was at the time of occlusion, where that light source was, essentially. And what we get here, now this is a real key aspect of this. What we get here is on this mountain peak in particular, and on all mountain peaks, when you go through the data set here, you'll see that there's a true position intersection difference. This is the angular difference between the star's true position and the predicted elevation for the mountain peak using rise over run. And if we were to change this cell, if we were to make the true position at the peak NA, it would break all the things that have to do with NA. And what you'll see here is that all the flat Earth stuff gets bricked. Now, down here on the globe, that's just because this is dependent on subtracting this position from this amount right here to get the difference. And now there's no difference because that position's been deleted, but this doesn't actually affect any globe predictions. This is just for a math check. But anyway, when you go down here, you'll see that the globe's predictions are unaffected and perfect globe is unaffected. That's by design. That's on purpose. Now, if we go down here to observer true position for what the globe predicts, because a lot of what we hear is that, why are you going into stellarium and referencing where the star or, where the observer isn't, because we want to see if there's a congruent triangle that corresponds to the light source and the elevation of the mountain peak with no drop over distance and the observer at the time of occlusion. Because the globe would predict a different geometric alignment, which I'll show here in a second. But anyway, if we go down here to the globe section and we were to change the true position for the globe, all of the globe stuff gets bricked except for perfect globe. Perfect globe remains because that's what's used to calculate you guys' predictions or whatnot, assuming the, idealized conditions aforementioned earlier, but not that anyone's disagreed with any of the mountain elevation predictions or anything like that. But this is the backbone of all of that. So when we're deriving elevations and distances based off of occlusion timing, it's based on the intersection where the globe predicted that star was for the observer in terms of physical elevation, which would be predicated on the drop over distance of this central angle between the observer and the mountain peak, because that's what defines distance. Just angle equals distance there when referencing all this. So the cause, so of this 27 arc minute central angle from observer to peak, there's going to be 13 arc minutes of drop over distance, which comes out to be 200 meters in this case. And, we just subtract that from the mountain elevation there, from what flat Earth would predict, and it comes out to be the same. And you can actually, there's a mode here to switch between flat Earth mode and globe Earth mode. And I currently have it set on globe Earth mode so that we're not straw manning the globe and using the subtracted half central angle from the rise over run to the peak, which corresponds to the identical, pretty much an identical angle. There's just some decimal place differences. But anyway, that is the bulk of it here. So when we look at this from a side view, I think this is the one. Yes. Yeah. All right. So when we look at this, we see that for the observer is what the angles for the observer are notated on the left here. The angles with respect to the peak are on the right side of this. So as the geometric intersection for the star at this time to be lined up with what the globe geometrically predicts for the peak, the 217 here, which corresponds to this time. So at this exact time, at 6:42:04, this star was geometrically aligned with what the globe predicts as a physical elevation for this mountain peak and for this observer to the star.
Wait. So you're saying that in the previous example, everyone agreed that in celestial navigation in practical terms, 69 miles per degree would be real and is a direct result of Earth curvature. But now that we're quantifying it in a direct geometric intersection, they want nothing to do with it, or they want half of it, or
no, they don't want anything to do with it, and they want to try and use the
Okay.
angle that corresponds to a congruent triangle on a flat Earth, not realizing the tacit agreement that the Earth is planar in that scenario.
Wow. Okay, just to be clear.
So the intersection window was missed here, and it wasn't until the true position of the mount or of the star was intersected with the peak did it become occluded. And then a little bit past that, oops, where's my, oops, it's the wrong one. All right. Anyway, a little bit past that, is our prediction for the idealized intersection there. So we were 2 arc minutes off trying to get it to rotate.
Just zoom out one step. It'll make it easier.
Oh, you're right. Now I moved it over here. Yep. Yeah. So anyway, the idealized intersection for us would be 2 arc minutes later, which corresponds to 11 Briel seconds. So all of the angles and times in here are converted. So you can see what they would correspond to in actual time. And then you can go into Stellarium and verify, was the star's true position aligned at this thing? Are they correct? Well, to help you guys out and to give you comparisons, if you go to the data table here, there are Canva links in column R. All of these links, if you open these bad boys up, let's take one and crack it open here, see what we got. We get true positions of stars for the observer, refraction on and off, and also for the peak. And then there was some early pictures taken where the refraction thing wasn't corrected or whatever. So in later versions, when going back and adjusting for the correct M bar and whatnot, the actual positions are there. So you can see the progression of change for everything. And then in more recent times, we added where the star would be for the idealized intersection to make sure that we're not, to make sure all our numbers are correct there when we're doing the time conversions and stuff. So everything here has been confirmed on our end, but obviously you guys are welcome to verify and confirm on your own. But check this out. So we got this intersection difference here. This is the crazy part. So we got our intersection difference here. 2 arc minutes. The globe happened to be off by 11 arc minutes. If you add these two together, it comes out to be 13 arc minutes. This is the half central angle. This is the 200 meters. The elevation that we derive when we go to derive elevations based off of the occlusion timings per our predictions come out to be 30 meters off. And for the globe, they end up being 169 meters off. If you add those together, that's the drop over distance for that. So completely independently, mathematically, we're tied to the same, like the air in our what we derive there. The difference in our measurements is shared by the half central angle prediction where the globe is supposed to be correct by this amount. So these numbers here are supposed to be reversed. Like the globe, if it hits its perfect intersection, they would be off by 30, or not perfect, but if they hit it like we were hitting it, they would be off by 30 and we would be off by 169. And that would change the timings to be, that would exactly correspond to an earlier occlusion timing. So, and let's see, there was, before we wrap up here, let me see how much time we got left. Okay. Before we wrap up here, there was one other point of contention on, let's see, what was it? Is it this? Nope. One second. Filipino notes. Yeah. This was just discussing the geocentric coordinates and stuff for eclipse predictions and whatnot. So when they get into trying to describe where the shadow is going to be located, they use Besselian elements, which uses the geocentric positions. It puts an observer directly in the center of Earth, and it lines up the positions of the celestial bodies with that exact center as well. And then they go from there. But all of that was just we went over that earlier, so we defined all of that here. And I think that here's the Besselian element conversion that they use. And there was one more. Principle of reversibility. Okay.
They use a fictitious observer at the center of the Earth
to give to basically, so you know how earlier I was talking about how there's a true position that's like this is where the light source was at one time. So in order to make an eclipse prediction, they need to accurately know where that position would actually be at that specific time of the eclipse. So they invoke it as a fictitious reference point to use where they can describe the angular change as if there's no refraction, but exactly line it up to where it needs to be to correspond to the 15 degree per hour position, the position that we don't see but is referenced as the apparent position, or referenced as the deviation from that. What's that?
So they do the observation from a place where it wasn't observed.
Well, they make the prediction for where it's going to be from a place where it's not observed. Yeah. And it's like,
that's unfortunate.
and it's, well, I mean, it's like, okay, when they do stuff like that, but when we reference where the geometric alignment was from Stellarium at the point of the mountain peak, it's like, you can't do that. But like the whole backbone of CellNav, as we just went over, is predicated on the geocentric transformation to link the celestial and terrestrial sphere together for it to be useful to have a causal mechanism for the 60 nautical mile per degree relationship. But let's see, there was another thing I wanted to touch on was refraction and occlusions. So I have some links here that talk about the principles of occlusion and what a virtual image is. So
Alan, hey, sorry, one sec. This is Pinky. Before you move off the Besselian elements, why were you bringing that up again?
Because they reference the true, they represent the true position of the celestial bodies to make the prediction, and not the apparent position.
Like the true Which true position?
As I defined earlier, the light source position. So like, when the source was above someone's zenith at 90 degrees, and then they just add 15 degrees per hour to that position, whatever that position happens to be.
Okay. That's just stellarium without refraction?
Yes, it is mapped to the celestial sphere.
But specifically, it's stellarium without refraction.
It's the stellarium is the celestial sphere.
Okay, so that's a yes. But like with refraction, it wouldn't be correct.
With refraction, it wouldn't be correct. No, they make
It'll change
they make refraction corrections, for the observer's location and stuff, like after the fact, but they derive the initial predictions for everything of where the shadow is going to be and stuff using the geocentric position, using that true position. And then they make refinements later. I actually have a quote from Fred Espernak talking about that specifically. Let me see if I can find it real quick. Let's see. NASA Eclipse Fred Espernak.
Part of why I'm asking is the thing you sent me last week about true positions, and it's why I was trying to ask this earlier, but I don't know if you say l'amazing or y'amazing, but they were saying that basically the stellarium unrefracted position was being considered an apparent position. There was a different true position that can't be found in stellarium.
Yeah, he was deriving a hypothetical elevation for what it would be based off of following the principles of how the angular position changes and what it's mapped to, in terms of nautical miles per degree. And then he was seeing if he could derive a consistent elevation based off of the time of occlusion, and the angle that's derived based off of the rise over run to that elevation using the shadow length as the run.
Right, and he's calling that true, and then he's calling the value that he used to calculate the heights. He was calling that the apparent. I would propose that you call that the height, or the what he's calling apparent we call true, and then we make another name for the other one. It's the truer elevation angle. Otherwise, it's going to be extremely confusing when we talk about it.
I don't think true and truer makes it less confusing.
Okay, I'm open to a word. I don't care what it gets called.
I don't necessarily disagree. We will take that into consideration. Where is the freaking Fred Espernak thing? Oh, here we go.
Hey, Alan, you're not taking off right away, are you? I wanted to ask a couple questions, but I'm still at work for about another 10, 15 minutes.
Oh, I got about 20 minutes left. So yeah, we are open to Q&A now though. The presentation hath concluded, but yeah, if you can get in any questions or whatever, and then I'll be available later. I'm just cooking dinner tonight, so I'll be back I can come back. Oops, was my mic muted that whole time? Did I answer anything?
No, you're unmuted.
Sorry. No, I have about 20 minutes and then I'm going to go cook dinner, but I can come back and answer questions if we're not able to get to you. I can check back in with you.
By the way, my question using the definition we talked about a second ago is why, with the eclipses, why does the trig not work out?
What do you mean? Why does the trig?
Meaning, like he takes the essentially the stellarium unrefracted elevation angle, and he uses that to establish a height of a sun and moon, and then he basically there's trig that goes back through the sun and the moon. You draw a line from the sun and the moon back to the point where the shadow's at, but that doesn't work. And so what he does is he says, well, that's an apparent position. Those are apparent positions. It doesn't work. and then he redoes trig to make another. That's why I'm saying a truer position, because the stellarium, what you're calling a true position, didn't work. So there's got to be it has to be corrected to make a more true position, or sorry, more true elevation angle.
You want me to take that, Alan?
Absolutely.
Okay, so my premise is that we see in curved visual space, and that our the way we see is what's mapping things to the celestial sphere, kind of like the sky is curved. So that would mean where we see things would be on the celestial sphere, but the physical location, which I'll use instead of true position, would be where the celestial objects actually are, but we don't see them there. Does that make sense?
It does, but why then would we not see, like, the place where we see the eclipse happen? Because the whole thing of celestial theodolite is, because I believe, based on the personal azimuthal grid of vision, the stars are never where we see them. They could be behind us, on the side of us, whatever, right? So there's like this other thing that moves stars around. But for the purpose of celestial theodolite on the mountain, if we go to stellarium and we get the elevation angle at the peak, that should work. My question is, why doesn't it work for eclipses? Why do we need an additional?
It does work for eclipses, but you'd have to get your observer from the moon, and that data is not available from stellarium. So I had to come up with an alternate method for having a lack of data.
Okay, I'll have to think about that. But
Why
then,
wouldn't
like,
we
my
observe on
response
the
would be
moon?
the method you came up with sort of is like, because the elevation or the height of the sun and the moon was calculated based on stellarium in the first place.
Yeah, so what I did was I calculated the radius of the celestial sphere, basically. And then what I'm assuming is that the physical coplanarity intersects with our sphere of curved vision at the zenith point. And then I just basically took that presumption and then checked to see if it was consistent throughout all the data points, and it was. So that's all I did.
Do you, like, would it be possible to just take whatever stellarium is, because stellarium you can change the elevation. I think Alan said that there's a limit to the height you can move it to.
Limits you to like 60,000 meters.
Right, but there somewhere in stellarium there's just a function that you could that we could probably extract to move that up to the height of the moon.
I'm not even sure that it's accurate, because it doesn't seem accurate when you adjust the altitude.
I know, that's the whole premise of the mountain peak. Like, if you say, well, we can't use it because it's not accurate, then why are we using it for mountains?
Well, it works in the case of mountains because it's on a smaller scale. But when you're talking about the height of the moon, that's like a order of magnitude difference, you know.
Yeah, but like, why would it be? I don't get that. I don't get why the
height of
moving it higher is going to break it.
Than the mountain. Like, we can actually go to a mountain peak, right? We can't go to the moon and actually verify the height. That's what he's saying.
And even in stellarium for Cell Theo, it doesn't really matter what you put the elevation of the mountain in, that it has minimal effect on the stellarium data.
I know, it affects the moon for sure, right? But it won't affect the stars. Definitely not the stars
on Earth, where that it matters. Like,
in the case of the star Cell Theo, the Cell Theo star observations, the height of the observer on the mountain is so insignificant to what stellarium is calculating that it doesn't have much of an effect. But in the case of the eclipses,
but that's because stellarium's calculating the stars like really far away. But if you're saying the stars are only a few thousand miles away, then there should be some discrepancy.
Who's saying that?
Well, we're saying the sun is 3,959 miles away. So I'm assuming if you did the same, if you did the same thing with the stars that you did with the sun for eclipses, you're going to come up with the stars are all 3,959 miles away.
Yeah, and we're saying that's all apparent and based off of a scale that's internally consistent, by deriving units of measurement from the system itself, etc. So, like, that's not the actual physical elevation. That's the calculated value of what it happens to be for the apparent position to follow the 60 nautical mile per degree relationship. It doesn't necessarily have to be at that physical elevation. In fact,
Where is it?
I missed that part. I thought you guys were saying that the sun is actually at that
No.
elevation.
nope, that's
Okay, that
never.
makes sense why you were confused.
Yeah, no, and to be clear, that's never been our position. It's that these are calculated values that we get out of this system. So
Right.
we've been
But I guess
arguing
like
the
when I
equivalence to
saw
that.
it, you guys did the spreadsheet where the sun was like moving. Yeah, I think you moved it back and forth, and the sun stayed at a fixed height or whatever. Like it doesn't seem as big of a win if that's just an apparent height.
It's always an apparent height. Like even like the elevation
But like you don't think the
change,
sun actually has a height above Earth?
not one that will know what it physically actually is.
But like in an eclipse, we do. Like I feel like the whole point was that during an eclipse or during an occlusion, we have a straight line to it, right? Because we don't have refraction, we're looking at the actual sun.
No, the premise was to plot out an elevation change in the based off of those angles. So if there wasn't any elevation change, then then the Earth's flat.
Exactly.
Okay, so you're saying like at the time of an eclipse, when we look up and we see the eclipse, we're not looking at the sun.
We're not seeing a physical elevation change in the celestial bodies, is what we're saying. So it's an apparent change in their elevation always. So the reason that the globe has a different geometric time is because that they claim that rate that or sorry, not rate. They claim that angle is based off of Earth curve. So it predicts a different geometric alignment for the observer based on that Earth curve if it were real. But it doesn't occlude when the globe predicts it. It occludes when that angle corresponds to what the elevation is if there's no drop over distance. So it takes a longer time, meaning that the elevation change wasn't physical for the observer that is seeing the star go down for them. It has nothing to do with the actual light source physically going beneath them. Otherwise, it would have occluded earlier.
Think about it like this, Pinky, right? The Earth is supposedly rotating. That's what's making the sky move, is us rotating. So if that's the case, then you would actually have a measurable change in apparent height. But since you don't see that, Earth's flat.
Why would you have a measurable change in apparent height, sorry?
Yeah.
Because you would be geometrically aligned with the elevation of the peak.
Exactly.
Oh, are you talking about like the fact that we're, when it's directly underneath you, you're a few thousand miles closer than if it's right at the horizon?
No. We're talking about when the true position of the star for the observer is geometrically aligned with the elevation predicted by the globe using, drop over distance. The same.
I'm just saying, like when you look, because I thought the whole thing is when you see it occlude, when you see two things occlude, that's the moment in time when you know you're looking at the thing, right? The rest of it could be apparent, it could be whatever, but you can't, like, I don't know, I feel like you've said there's like a little saying you say about not being able to occlude a shadow or something like that. But so like my understanding is that when you're looking at the eclipse, that's the moment when you know you're looking at the actual eclipse. I thought that was my understanding is that was the whole premise of it.
Yep, I also understood that way, and I feel that the story simply changed because I asked about clarification for that many times. He repeated to me that same exact explanation, that this is the reason why they ignore refraction. That because like this was the entire point of the celestial theodolite. Because if this wasn't eliminating refraction, then you would be able to just take an angle using an actual physical theodolite without any references to any stars and any complicated bullshit like that. And the entire reason why they are doing this more complicated method is because it eliminates refraction. That was the entire point why this method was invented in the first place, according to them. And I feel now the story is changing because the angles simply don't match.
Story's always been the same. And actually, when you asked me about that specifically, to come here and say that this was a different story, what did I tell you specifically about why we change position or why we reference where the star is for the mountain peak?
Because you cannot, because after the star is obstructed, then there is no light to refract. That is what I heard.
We are interested in the geometric alignment with the cause of the occlusion. Right? Our premise is that using the true position as a light source and geometric intersections, we can make mutually exclusive determinations on the shape of the Earth based off of how they line up for occlusions. So when you take a triangle, right, and that true position is lined up for the peak at 2 degrees 31 arc minutes, and that also corresponds to the exact time that the observer stopped seeing it when that intersection occurred. That makes a congruent triangle from the observer to the mountain peak at 231, and then a triangle from the mountain peak to the star at 231. That time that occurred should have occurred much earlier if the Earth were a globe. They would have had the 217 intersection time, because that's when it would have been aligned with the observer geometrically from the peak, or from observer to the peak, and then from peak to the star on a globe. You don't get to have
earlier.
Yes.
Wouldn't that be the exact opposite way though? Because the Earth, if the Earth was a globe, then it would be dropping over distance, and that would be influencing the angle you would measure to the peak. And in order for the occlusion to take place, the angle to the peak has to equal the angle to the star. So the star would have to travel a bigger angle in order to meet this peak that would be lower due to this curvature of the Earth, and that would be some additional time.
No, for the geometric alignment to occur, this is why we have the canvas slide. For the geometric alignment to occur for the observer, if that elevation change is physical, then it's going to be geometrically aligned with the peak at that earlier time, because it already experienced that drop over distance. That's
okay. So maybe geometrically aligned is the phrase I'm looking for. Because that means, like, to me, geometrically aligned means that there's a line between me and the sun, right? At the point of eclipse, there's a line between me and the sun, a straight line.
Okay. Can you show this slide with the smiling globe for a moment? Okay. Now imagine that, like, let's don't change anything about the stars for a moment. But let's imagine that instead of a globe, the surface is flat. Like, let's say it's horizontally flat in this coordinate system. Then the mountain peak would also be higher, because there wouldn't be this drop anymore. And it would already be occluding the path of light to the observer. If you imagine, like, completely straightening out the surface, it would already be occluding that. So that means the occlusion would take place sooner on a flat Earth than on a globe.
The opposite. So if you're on a globe and you got your regular theodolite out, right, and you're looking at this mountain peak at 217, right, obviously it's going to be refracted. You would say 219, but the actual geometric angle that you would add the 2 arc minutes of terrestrial refraction to would be 217. Okay, the time at which this star is geometrically aligned at this same angle is at 217, and it's at 1842.04. That's when they're geometrically aligned. Now, if the star isn't physically changing in elevation, then it gets to keep going until it's aligned with the peak at 233, or thereabouts, and that's when the occlusion happens. So if the elevation change were actually occurring, the star would have already been occluded. There's a massive difference. Oh, it's on this tab. 1 second. There's a difference of, let's see. There's a 1 minute and 3 second difference in intersection time based off of that. That's when these two were geometrically aligned.
Okay, I feel like you're I pointed a very specific, clear example, right? A thought experiment. they feel you didn't address it at all, and instead start talking about some very ambiguous words, like for example, the star having a physical change in elevation. What does that mean? Like, does that mean an angle is changing because you have elevation angles? Does that mean
that's exactly
the
what it
physical
means. It means its angular elevation
distance?
is changing, following 69 miles per degree. Remember earlier when I asked if anyone had any contentions to the relationship of 60 nautical miles per degree in Earth curvature, and you specifically said, I agree, and everyone else also tacitly agreed in their silence? So if the cause of the elevation change is that, then the geometric alignment is earlier for the observer. Yes.
If you want to claim that what we see with the celestial sphere, what we see with the stars, is equivalent between flat Earth and the globe Earth, then the stars would behave the same exact way on a flat Earth from definition, because it's supposed to be equivalent. The only difference will be on the surface. You would observe the star at the same angle, or else it wouldn't be equivalent, or else you would predict different angles to the stars themselves, like completely ignoring the surface. If you only take a Theodolite, measure an angle to a star, then according to your idea, you would measure a different angle on the globe and on the flat Earth. But at the same time, every time we point out those differences between those models, you say, no, they are equivalent, it's just a projection. I think you're holding two different positions that contradict each other at the same time.
No, it's the exact same position that it's always been, number one. And number two, your occlusion time is based on the geometric intersection for the observer. Remember when everyone was like, you can't reference the mountain peak. Why are you teleporting to the mountain peak? The entire globe, as we just went through, is predicated on the geocentric position transformation, all of that relating to the positions of the stars when they're angularly intersecting. Okay, if the conceptual model of the elevation change of the positions of the stars was truly because the Earth is curved and it's following this curve based on this timeline, then it would intersect physically at an earlier time because it's observer based. But what's happening is that there was no geometric alignment, and you guys have been arguing that it's refracted over that to meet the flat Earth position. You guys are changing your position now that you're confronted with actually dealing with the angular intersection difference. You guys are actually trying to change it to say that this should go on longer, and that the flat Earth would predict it sooner, when it's already geometrically aligned here. This is why when I say, you can pull up Stellarium and verify all of this, this is what I mean by that. This is the angle for the peak at that time. This would be for perfect. But if we go back to observer here, the time was the observer, let's see, 4204.
If you just find a really simple version, on a flat Earth, the observer location would physically be higher, changing nothing else about that. So you'd expect to see the star for longer.
Hey, can I get some clarity here? Was it the claim that with identical skies, the star should be occluded earlier on flat Earth compared to the globe? Is that what's being claimed?
No, he's saying the opposite.
No, that was my claim, because
I'm asking what you were guys saying. Yeah, what are you guys saying? Are you guys saying that the flat Earth will occlude first, or the globe will occlude?
I'm saying that the globe occludes first because it's based off of the observer's location and their geometric angle to the star. So at the time the star is at geometric alignment with the peak, the time is 6:42:04. That's when it's at 217, and the geometric elevation for the peak between this observer and the peak is 217. Now, no occlusion occurs. They say it's refracted up. It just happens to be refracted up long enough so that when it geometrically aligns with the peak, with no drop over distance for the elevation, that it just happens to line up with the occlusion for flat Earth. That's what that's what the argument is.
I'm not even talking about like the specific angles or time. Just the fact that you're expecting the globe to occlude the star earlier is already
because of Earth curve, Bacon. Because of Earth curve.
Yeah, I totally agree.
Yeah, let me just finish what I'm saying. I'm just trying to wrap my head around that, because if we have identical scenarios, the only difference is one, the mountain is dropping, the other one, the mountain is not. How is the dropping mountain occluding the star first?
Dude, I had the same. I had the same confusion. I think I understand now, though. So it's because it's about the alignment of the three. I was also thinking what you're thinking, what you and what the other guy was thinking, that like shouldn't it happen later on the globe, because the globe, the mountain is dropping physically on the globe, so the alignment should happen later. But I think the alignment on if the elevation, that now when they said the elevation doesn't change, that's what they're looking for, right? So the elevation doesn't change, the alignment, that angle will happen ostensibly later on the flat Earth as the star travels away, and its angle changes that way.
Why
but
though?
we're
Like all
using
you're
the-
doing, the only thing you're doing is moving the mountain up. The star stays the same. Stars don't change angle. Like that's all fixed.
we
That's
have-
in stellarium.
If we're using the unrefracted, but if we're using the unrefracted direction to the star for both models, then of course one where the mountain is higher or physically higher, it would intersect that direction physically earlier.
I could be wrong, but I think it's because I'm just thinking on the spot here, right? Because there's two. It seems to be two different, and they can correct me if I'm wrong. Because let me finish what I'm saying. The angular change, if the elevation, if on a flat Earth where the elevation doesn't change, would be happening for a different mechanism, aka the star traveling further away. Whereas on a globe, the angle would be due to rotation and getting
Okay.
That's not the point.
But the entire
it's exactly. Oh, 1 second. It's exactly the point. Not just rotation, but the curvature along that central angle between the observer and the mountain.
Oh, but if we're agreeing that the unrefracted angle is the same, then it doesn't matter what the mechanism is for that unrefracted angle. The unrefracted angle is the same in both, then the mountain that is higher would obviously intersect that first, regardless on what's the mechanism for the angle of the star. Yeah, that's not making sense to me.
Dude,
I think we
listen,
have to-
listen. You go into Stellarium right now, enter the observer coordinates, and enter the time 184208. That's when the star's true position is geometrically aligned with 217. So like, there's a lot of hypotheticals and what ifs right now, but the time is literally in Stellarium. We could all look at it. This is when these two are geometrically aligned, as my boy Babby pointed out. That is the difference, because they're saying that the change in this position is due to Earth curvature, the same as the reason that the elevation of the mountain is changed. So when these two geometrically intersect, there should be an occlusion. It doesn't happen later for you guys. It would happen sooner.
Bro,
I'm not.
I feel like you're just
Go ahead,
avoiding.
Mo.
I think it's a totally valid critique.
Geometrically impossible. Geometrically impossible.
So I think we have to ask a very.
What's impossible?
Hang on, let Imbo speak. He's trying to. Yeah, go ahead. Sorry.
Thank you. I think we have to ask a very specific question here. Does the flat Earth side here believe that the sky will always behave in the same way as we would predict on the globe? Like, given latitude, longitude, and the time of the observation, will you observe like every single star at the same exact angles as you would predict on the globe? If the answer is yes, which means that both models are equivalent when it comes to the sky, then the flat Earth would occlude quicker than the globe Earth, because we don't change anything about the sky between the two models. The only thing we change is the grant, and the grant is dropping on the globe, which would mean the angle would be lower. The only way this could happen earlier on the globe is if there was some different model of the sky on the flat Earth than on the globe Earth. And in that case, you would have to provide it, because Stellarium is the model that is equivalent with the globe. The only way you can use it is to declare that your model is equivalent with the globe. I don't care about what the cause of it is. I'm only caring about the effect, but you still have to accept the effect that it will be the same angles as on the globe. But if you're now abandoning that position, you cannot use even Stellarium anymore.
No one is abandoning that position. 1 second. There was a whole bunch of stuff that was just bastardized. So Stellarium is using the exact same model that we just went over in the beginning, which isn't mutually exclusive to anyone. It's based off of the apparent elevation changes of the celestial bodies, the apparent angular elevation changes. Now, to test whether or not these angular elevation changes are physical, there's going to be a geometric alignment to a mountain peak that is a specific elevation due to the drop over distance between the observer and the mountain peak. The star is going to be changing elevation at 15 degrees per hour. It's going to, for the observer, which this whole thing is built upon, where these positions of these bodies are, we're not changing things up. We're not doing a different thing, referencing the exact same system that's always been referenced. For the observer, the globe predicts that this elevation change occurs at this time, 1842.04. We can go into Stellarium right now, which I just changed it back from at a different time, but I sent you the screenshot earlier, so you know it's correct. That is the elevation and time that those stars are geometrically aligned. To my man who shouted out, geometrically impossible from the crowd. We're looking at the geometric possibility right here. We're looking we're looking at Stellarium right here, showing the geometric alignment at an earlier time. If the time on Stellarium says that it's earlier than the time of occlusion, is it geometrically impossible, or did it already pass its time of intersection?
Well, the argument isn't even related to this.
Geometrically
Oh no, it's specifically related. So you're telling me that the software that you think proves the globe that's giving an angle at a specific time, you're saying that that's geometrically impossible. Respectfully, sit down. Who was who else?
I would like Leftlin to explain why it's impossible with detail, please, Leftlin. If you say it's impossible, you need to elaborate. No, can I finish speaking?
You're being so loud.
A question, Rob.
Yeah. Can I finish? If you're gonna just say it's impossible and say we'll ignore you, unless you're gonna elaborate on why it's impossible.
If you need me to elaborate, then you gotta. That's your problem.
I just got a quick.
No, it's not. You can't just come into the You can't just baselessly assert something's impossible.
Have you not met Leftlin?
I think Bacon was going to explain.
Can I ask a question
Hey,
real quick?
no, hang on. Let me respond to what Alan was saying.
But I still think you guys should hold that plan feet to the fire.
This is all related. It's a question for you. So can you just answer me this? Are you in agreement that an observation was made?
Who are you asking?
You. Are you in agreement?
I haven't asked my question yet. I'll answer you. Let me ask mine first, because I was trying to ask before you started.
Okay, go ahead.
All right, thank you. Yeah, so what Imbo said wasn't even related to any specific angle or time. It was just due to the expectation that the star would be occluded first on the globe. While you also said the model using star isn't exclusive to the globe, which to me suggests you want to claim the same model on flat Earth. If that's the case, if we have the same unrefracted true direction of the star on both, then one where we drop the mountain, like if we wait until the mountain occludes the star and we stop time there, then there's an alignment on flat Earth. Now, if we switch the globe, that drops the mountain, so the star will no longer be occluded. I mean, I don't see any response to that besides going over the angles and values again.
Well, that's the whole point, though. See, the hypothesis of the whole deal is a null hypothesis, which is the Earth is not flat, right? Or is flat. Which one is it?
So your hypothesis is that the Earth is a globe. The null hypothesis would be that the Earth is flat. It's always the opposite.
So then all they're doing is making the observation. So, I mean, are you arguing that the observation is incorrect? Because that's really all they're freaking doing. There's no expectation of anything.
There is. He just said that the star should be occluded earlier on the globe. That's an expectation. That's what's not making sense. If you want to compare globe with flat.
Bacon, what time is it on my Stellarium right now? What time does it say?
Let me see.
Can you read that?
Yeah, 1842.
1842. Can you read the angle here where it says Alt as? What does that say? Is that
2 degrees, 17 minutes? Sure.
Okay, cool. Now, let's see here. What is so the globe geometric prediction for the peak does that say 217? 217, is that what they predict?
Yeah.
So at 217, that star was geometrically aligned at 8:42:04.
You're asking if that was the time in the story?
Yeah.
I already forgot what the time was. Can you go back to story?
Yeah, no problem. No problem.
And to be
Yeah.
clear, with because the globe's prediction
That's
is
the
not
same.
without refraction.
Oh, 1 second. You guys want to change back to refraction? We can go there. Give me 1 second. We're doing this real quick though. Go ahead. You said 18:42:04. Okay.
I don't think we should do this. I think we should finish
I
this
don't
topic.
think you're really in charge of anything around here. It's interesting that you thought that though.
You
But
know what I'm in charge of?
no, you know
I'm in
what?
charge.
You know what you're not in charge of? Interrupting a dialogue between me and my boy Bacon. Bacon, go ahead, sir. So the geometric angle at 217, also the star's geometric angle for the observer, its true position was 18:42:04. Agree?
I forgot the seconds, but yeah, it was 1842.
Yeah, 18:42:04. Right. So this is when they were geometrically aligned.
Okay.
And then the time of occlusion was 18:43:07.
Okay.
So
how does that relate into my question?
it relates to your question in that the observer predicted the geometric alignment at this earlier time. This is how we got here.
Well, my question is how the comparison between the globe prediction and the flat Earth prediction expects an earlier occlusion for the globe. That's my question. I don't think how that can relate to
It was just the Earth curve in between that central angle. So the central angle between the observer and the mountain peak there is 27 arc minutes. Of that 27 arc minutes, there's 13 arc minutes of curvature, which corresponds to 200 meters. So there's 200 meters of drop over distance that occurs as the star makes its transit of 2 minutes and 30 seconds to cross this 27 arc minute central angle, so that it will go from for the observer, so that it'll go from 233 to 206. This is how long it takes: 2 minutes 30 seconds. At 1 minute,
if you move the peak down,
please. Oh, you just gonna start talking in the middle of me explaining this real quick?
I would lie. I do have a question. I'll ask once you're done.
Super
I'll
cool.
ask once.
Thanks, dude. Wait till you're done then. Okay, so at 1:15, as it's traversing this half central angle, this is the Earth curve that it's traversing here. So there should be a geometric alignment there at this 217 as it's lowering in elevation for the observer.
Okay, the Earth curve drops the mountain down. How's that making the star being occluded earlier? I still don't see how you're reaching that.
The geometric position of the star for the observer is lower earlier. So if the mountain peak is at 217, then the star needs to be at 217 for there to be an alignment there. It's not like this is
I don't know how you're getting the.
This is considering the drop over distance for the mountain. This is what causes the mountain to be 217 rather than 230.
Like you're saying, shouldn't they be the same? And we're saying no, they should be exactly different by the amount of Earth curve over that distance separating the two models' predictions, right? You understand that? This is 50.7 kilometers, so that's 201 meters of drop. What your prediction should be different from our prediction by exactly that amount. Do you not agree, Bacon?
I don't know what you just said there. Which one is that peak?
The globe geometric peak is F11 here.
Okay. If the coordinates there on lines 22 to 25 are correct, then you just got the exact same that I used in my prediction for the globe, which was within a second. So I don't know how you're getting that this is a minute wrong.
So when we derive the elevation of the mountain peak based off of the occlusion angle for the based on the observer's position for the true position, we're using 206. They end up with an elevation that's off by 169 meters. And when we do the elevation for flat Earth using arctan rise over run to the occlusion angle, we're off by 30 meters. If we add our differences together, we get the globe drop there. So these should be reversed, and they're completely independent of one another. I don't know if you saw it earlier, but I went over how everything is derived and the two variables that drive each predictions. This air that we share in elevation is in relation to the half central angle here, which is the predicted drop over distance.
Okay. Yeah, I'm just saying there's something wrong there, or at least maybe my math's wrong, but maybe you could point that out, because I predicted the time of occlusion. I didn't use the time of occlusion to calculate any angles. I just used the coordinates of the mountain, the observer, the altitudes, all that, to predict the time of occlusion. And for that observation, I'm within a second. So I don't agree with your prediction that there's
You got your own method?
You'd have to show me your math there, but what time did you get for the occlusion based off of what the globe predicts for angle? And did you predict 217 as the physical elevation?
The time I have here for the actual occlusion is, let me see, 43 minutes and 7 seconds. Is that the one? Is that the right time?
That's
observed?
That's the actual time of occlusion.
Right, so my prediction was 43 minutes, 6.4 seconds. I can drop my math if you want to take a look at it.
Please.
It's just a script. Yeah. I'll drop specifically with that.
Because Rua's prediction was also 217, all things considered. I'm sure you guys usually agree.
I haven't checked anybody's work, I just did mine. But yeah, sure, let me...
Well, the thing is, the observation was made, so the time and the angle and all that, I mean, that the data tells the story.
Well, yeah, it should be independently corroborated, though. You should arrive at the same conclusion as Ruhif, is what I'm saying.
No, I'm better at math than Ruhif.
Yeah, but Ruhif will just make it a Python.
I'm just kidding. I'm just
that
kidding.
way.
I did a JavaScript script, so it's not that far from.
You're not kidding.
Yeah, I just posted the whole math.
Thank you, sir.
You're welcome.
I'm confident you guys will end up agreeing on this specific point.
So, in my opinion, all of this is overcomplicating a very simple issue. So I've seen that in the canvas, like where you have this smiling globe slide, there are actually tools on the side that you can use to edit the slides. So why wouldn't you just be able to draw a flat surface on the top of that globe to compare it with that globe and draw a mountain of approximately the same height as this one, like a triangle of a similar height, and then rotate the stars as you did with the globe and see which one is going to occlude sooner. Is it going to be the flat Earth or is it going to be a globe Earth? Because that's a very simple geometric problem. In my opinion, it would be easier to visualize it using geometry instead of semantics.
Do you have a problem with the
make
method?
it yourself. No, he should make it. You should make that, Embo. Go ahead. I would like to see that animation.
Do you want me to do it right now? I mean, I can, but like here we already have a ready globe.
Was that a hypothetical as an objection? It's a weird form for an objection to take.
Yeah, it's just to demonstrate. It's just to test because you have this claim that it would occlude sooner on the globe, and this would be a proof of that. It would be a test that we could use to differentiate if that's actually true, or would it be the other way around?
Are you saying that this doesn't represent the globe and their intersection time?
It does, but in order to test if it's going to occlude sooner than the flat Earth, we also need the second Earth. We need the flat Earth for comparison. We already agreed that the sky is going to be the same because it's equivalent, so we don't change the sky, we only change the surface.
The elevation change. Go ahead, Brian, what's up?
all you have to do to fix your model right now is move Nicki Minaj to the crosshairs at the center of the celestial sphere, and then rotate the mountain so it's 90 degrees up.
All right.
And then put it on that horizon.
All right, guys, you ready to go through a Canva run? All right, highlight Nicki Minaj. She's tied to everything, so
He's like, I noticed on the left you have tools and you can change stuff. So why don't you do this whole different comparison to see if what's reality is reality? Hold on. Let me grab a fresh Nicki. This is pretty good.
Do a copy of that whole thing just in case.
Looking at Shane's GIF or GIF.
That's by the way.
Oh God, you thought debating the flat Earth was bad. Try to pronounce that word.
All right. Okay. Nicki Minaj is now in the center. And then rotate the mountain up 90.
Don't even touch the stars. Just leave them exactly where they are.
Oh, gotcha.
And then take the mountain, and then move it.
Like that.
Yeah.
No, you need Nicki. You need
move the mountain. Now take the mountain and move it onto that red horizontal line.
You've got
Why are you moving the
picture
mountain
stars
down?
in different locations between the two models. You got to be.
Yo, relax, guy.
I'm already kind of confused. Why is she at the center of the Earth instead of at the surface?
Yeah, that was
that's the flat Earth model. At the center of the celestial sphere.
But this is not the celestial sphere.
It's always been the celestial sphere. But anyway, let's see here. Mountain. How do I get my mountain? There we go. Mountain. Said move the mountain down here.
Yeah, and then maybe a little closer to Nicki. Yeah, about right there. What you'll see is the stars are now higher than they were before because of the change of the center of the celestial sphere by the Earth radius amount.
You basically teleported the observer to the center of the Earth for absolutely no reason.
Embo, do you know that your model results in a fictitious observer at the center of the Earth? You know that, right?
like, bro, you know,
I mean,
we've
that's
been.
That's
you
not
know
how Besselian elements work. But
dude,
we can talk about that later.
It's not. It's not how Besselian elements work. It's not even just Besselian elements, though, right? Like there's a literal term called a geocentric transformation, which refers specifically to that. We read it right out of the intro from the Umblin document in plain English, in super plain English.
I don't think Embo knew that. That's all right.
But
help your boy out, Bacon.
In any case,
but this whole thing that you're doing right now, it's not like all you have to do is just straighten that pink and white dotted line. Just make it perfectly straight. Keep her right at that normal of the circle, and then connect the mountain to the end of it, and then you'll see. And the whole point for me is that, like, if you move the mountain up, it's going to occlude earlier. Like, it's so obvious.
Yeah, and the whole point for me is that if the Earth is a globe and the stars are changing positions based on that, then it's going to geometrically align at an earlier time, as confirmable by Stellarium, irrespective of what you think or how it should work. Like, you either believe that they're we're just gonna go right in the middle of what I'm saying, and then you're just gonna say a thing too. That's super dope, dude.
We're just talking.
I love it when people do that. So anyway, there's either a physical change in the angular elevation predicated by Earth curve, or there's not. So if there is, then this occlusion time is going to be earlier, and the numbers that are derived based off of that occlusion time would look like this. They would more closely match what the actual prediction is, doing globe math to the elevations of the peak using the drop over distance. It would correspond exactly to what we're deriving, only it would be on the globe side and we would be on the side of air. So that's the actual issue here. This whole rigmarole of like, oh, we have to go to a different thing and show you a different model of how it would work. Bro, it's the same model. It's just showing that the elevation changes are apparent for the observer, which is what the whole thing, which is what we just based it on, is based off of. That's why we reference the change in position of the mountain peak to see where the geometric alignment is at. Is it with what we predict? Because you guys missed your window. If you're having a hard time, dude, we're 20.
You know,
we're almost 30. We're almost 30 weeks into this, and you guys are just now getting to this. Like,
I noticed when Bacon wasn't looking at this image directly, he confirmed all the times and angles independently of the image. And then I guess when you're not looking at the implication of the image, then you can do that. But when you look at it, you go, "Ooh, nah, I don't like that. I don't like how that looks."
Something's wrong here.
But
What do you mean?
Can I go now? Or just let me know when I can go.
yeah, you can go, and then we're gonna wrap up because I gotta go do dinner.
Okay,
We'll
like
be
it just
back next
seems
week.
you don't have to look at a picture. You just say on a globe, Earth is going to curve down, the mountain's going to be at a lower elevation. The sky, to Embo's point, the sky stays the same for both models, right? The stars don't move based on what the ground's doing. So if the mountain goes lower, it's going to occlude later.
The stars don't move based on what the ground's doing, bro. That's completely against central angle theory.
Stars are like
that's exactly what the motion
I'm
is
just saying
predicated
stellarium.
on.
Hold on, it's my turn. It's my turn now. Just let me finish. The stellarium, the angles in stellarium are fixed. It doesn't matter if you turn the ground on or off or anything about that. Those angles stay the same. So if the mountain is higher, it's going to occlude earlier.
If you turn the ground on or off, bro, what are you talking about? That fucking elevation was literally at an earlier time. That's it. There's no there's no mysticism magic to it. It's what time was it when they were geometrically aligned with the physical angle that the globe predicts for the mountain elevation? That's it. I have no idea what you're saying. To turn the turn the ground on and off, bro. The mountain is already the mountain angle is already calculated. It's already considered.
All I'm saying is the mountain's lower, it's going to occlude later. If the mountain's lower, it's going to occlude later.
If it's based, if the change in elevation is truly based off of the observer and the Earth curve in between them, then it would be sooner. So you're now abandoning your position of globe curve. That's nice.
But we're not using different angles to how high the star is in both flat and globe. If you're using the same angle to how high the star is, and in one of those two the star is higher, then the mountain is higher, then of course that's going to occlude the star first.
We predict different elevations. Why would it be the same? And one is specifically observer based, saying that the cause and the change of position of the star is it's physically getting lower because of Earth curvature. So now you're saying that that's not the case and that there's no distinction between our models. That's incoherent AF.
Wait, no, that's what I thought you guys were saying. When you said there is no difference in elevation angle, are you referring to the angle to the peak or the angle to the star?
I don't think anyone said that there's no difference in elevation angle, man. I don't know what I don't know what you're talking about.
Is there a difference? Is there a difference in elevation angle of the star between globe and flat Earth for the time of occlusion?
Yes, when using these celestial sphere models, they make different predictions based on the physical elevations. So on a globe following the celestial sphere, which I brought up earlier, which was just stellarium, the angle at the time of occlusion is 217, and the time that corresponds to that for the globe is 1842.04. We read it directly, we went over it, and you were like, yeah, agree.
Yeah, what they're not going to say is you've been saying for the past hour that you have to go make dinner. I don't want to hold you up. Why don't you go ahead and do that? That's not what they're going to say, because they're inconsiderate assholes in here.
So let me ask
you want Alan to leave, just tell him.
If you got a man, you're standing there, it's 8 p.m., you take an angle to a star, you're on the globe Earth, you take an angle and you go and reference it and you get that angle. Then you're standing on a flat Earth, same time, same location, you take an angle to a star. Where do you get that information to see what that angle should be?
By going out and actually making the observation.
If you change positions,
I just did. Did it change on a flat Earth than it would be for a globe Earth?
If you change positions, the reference to where its elevation is will change. That's why we reference
Nope.
that's why we that's what buddy. That's why we reference the true position at the peak for the occlusion to see if it intersects with what we predict versus what you guys predict from the observer base location.
Can I ask another question?
I don't think he has you turned up, Ruhiv.
No, I have Ruhiv muted because he's just in here linking the same image that we go over every day on Telegram about. And then he just says, what you're doing is rubbish, mate. And like he doesn't need me for that. Like I can just as easily not interact with him, leave, and then he could just say it's rubbish on his own.
So you're mad that the observation doesn't match the globe.
Oh, to my prediction, it does. Yeah, to my
Dude.
prediction, it does within a second.
Yeah,
but
well,
let me just
yeah.
ask a clarifying question with the last thing you said, if that's all right.
Go ahead.
Okay. Yeah, are we not using the same prediction for the true elevation angle of the star between globe Earth and flat Earth, given a specific timestamp?
What did you say?
Given a specific timestamp, are we not using the same true altitude of the star for both globe and flat?
Same timestamp. We're referencing different positions. So for the globe, they're referencing where it is for the observer because that's where their geometric intersection would be. For flat Earth, we're referencing at the same time at the mountain peak.
No, forget the mountain peak. Given a specific timestamp, the true elevation angle of the star, should it be the same on both globe and flat?
Oh, just in general or whatever.
Yeah, given a specific point in time, if I want to say what's the elevation angle, the true unrefracted angle to a star.
Yeah, sure.
Would that be the same?
Yeah, sure.
Okay, so if the unrefracted angle to the star at the timestamp of the occlusion is the same for both flat and globe, and flat has a higher peak, then how is the higher peak not occluding the star earlier compared to the lower peak?
Because it would already be geometrically aligned with what the globe predicts from the observer-centric position, not accounting for looking at it from the reference of the peak. Because like the whole thing was that it just happens to line up with that, and they were content with saying, we're not going to use the angular difference from the true position. We're interested in the refracted position, which ends up being over the peak at the time of occlusion. So they end up cutting themselves short on various amounts of astronomical refraction to exactly match, the angular difference that was measured from flat Earth. But in any case, that's where the actual argument's been. This is the first time anyone's tried addressing the actual geometric intersections. So you guys are all saying that it would be a different time, but then you're happy to try to co-opt the later time with refraction on the opposite end of it. So the argument has always been this, just no one's ever gotten to this point because it always gets obfuscated and derailed. So this is where we're at. This is where we've always been at, the geometric intersection difference between our two models, and how independently, when we take the air and the elevation that we derive versus what the globe derives, we end up with the half central angle, which should be the drop over distance, which should have made the geometric alignment correspond to the earlier time given by the globe. So with that, if anyone wants to get some closing thoughts off or whatever, feel free. But I'm going to wrap up here in like 5 minutes. So this is just for you guys.
My closing thoughts are when you edited that image, the entire reason why you edited that and teleported Nicki Minaj to the center of the Earth was because it changed the angle to the stars compared to an observer at the surface. But the premise was that the sky is equivalent of models, so the angles to the stars wouldn't change. So why did you have to do that in order to prove your point instead of keeping the observer at the same location, so the angle would be the same?
Because a congruent triangle based off of the intersections of the light source and the observer would be different on a globe. It would be at that earlier timing.
No, it wouldn't. if we agreed that the sky is going to be the same, in your demonstration, you didn't agree with your own premise, you edited the location of the observer to have a different angle to the stars, because in your drawing, the stars aren't infinitely far away, they are pretty close. So, you know, changing the position of the observer will change the angle to them.
Yo, actually trying to conflate the supposed actual distance to them in 3D space has nothing to do with the use of the conceptual model that dictates 60 nautical miles per degree. That's all bound by the geocentric transformation, which introduces the central angle and half central angle for the Earth curve relationship. For there to be a change in angular position over distance. You guys are, yeah, all right. All right. Bacon, I will get back to you after I check out your math thing, and I'll let you know what's up with that. I appreciate your
Alan,
your time and effort there. What's up?
Thank you.
just I never got to get to my questions.
Oh, yeah, sorry, go
But
ahead.
next week, yeah, no, it's no big deal. I know you got to go in. I know you stayed late to answer a bunch of shit. But next week, I just want to go over some celestial observation questions I have about what we should see. But it can wait till next week. Thank you, Alan.
All right, no worries, man. I appreciate it. We'll see you guys next week. If you have any questions in the meantime, also tag me during the week or whatever, and I will make a.
Nobody wants to talk to you, Ruhif.
I'll make an official page answering the questions or whatever. All right, lads and ladettes, join us tomorrow night. We're going to be watching Bennett's interview on the, I can't remember the guy's channel, so sorry. But we're going to be watching an interview that Bennett did recently on Ether and mainstream physics. So check that out on Tuesday, tomorrow night at 8 p.m. Eastern, 6 p.m. Mountain, and 5 p.m. PST. And then we'll be back again on Sunday for a presentation on Globebusters featuring Vambi. He's going to be doing a follow-up on refraction and demonstrations of image lifting in the lab. So definitely tune into that on Sunday.